So today I'm going to talk to you guys about something Autodesk has been working on, and more specifically Fusion 360, and that's the convergence of design and manufacturing. So I lead a research team for Fusion 360, but I'm going to do something that's a bit unconventional for me. I'm not going to talk about research today. I'm not going to talk about features that are coming in 6 months or a year. I want to talk about things that you have immediate access to. And the reason I want to do that is when you're at a conference like DEVELOP3D, or just reading a lot of the industry news out there right now, there's so much change happening in our industry. Everything from additive manufacturing and generative design, advanced simulation technology, robotics, the connected factory. And the reality is there's no way to effectively leverage a lot of these technologies together when you have a disconnected design and manufacturing process. So my goal today is for you to walk away having a really clear picture of what's possible when you converge design and manufacturing with real examples, how Fusion 360 is 100% committed to supporting this convergence, and what it ultimately means for you, what it means for your process, and maybe more importantly, your time, so that you have more creative freedom to do innovative work. So I promise to stay grounded, but there's always a but. I do want to show you one of the craziest applications of this technology, because I think it's really inspiring to see what's possible. Autodesk is working with, no? Oh, all right. Sorry about that. Autodesk is working with NASA's Jet Propulsion Lab to reimagine what's possible for a lander to go explore farther into space in the search for life on other planets. And the thing is, spacecraft are some of the best engineered and highest performing things that humans have ever designed, and we need them to do more because we're finding very little signs of life on Mars. So we need this specific lander to go 10 times the distance of Mars to the moons of Jupiter and Saturn. So JPL needed to rethink their whole design process, to come up with a new strategy, and they decided to go with generative design. And because generative technology in Fusion 360 is manufacturing aware, JPL was able to not only explore many different part designs, they were also able to explore a range of different materials and a range of different manufacturing methods so that they can make the best decision for any given part in the system. So for the legs of the lander, they wanted to go with a proven strategy. They went with a qualified aluminum material and constrained the problem to end up producing a 3-axis milled part. For the body of the lander, the external structure, they end up going with a sandcasting strategy because of the complex topology and the sheer size of the shape. And now for the internal structure, because that particular part needed to be optimized to hold up 10 times its own weight, they decided to go with additive. Now, when JPL started this project, they hoped, could we get to 10% mass savings? Because every gram saved on this lander can propel that thing farther into space. The final design achieved 35% mass savings. But the thing is, this isn't just a weight-saving exercise. This allowed JPL to be more flexible in their design process because their engineers could embed design intent into the product definition. So by tightly coupling their process with generative technology, JPL didn't lock themselves into a particular manufacturing method or a particular material super early in the process. They were able to focus on their design goals and make effective decisions all along the way because Fusion took on the burden of exploring materials and manufacturing methods for them. Now, we don't do projects like this to build spacecraft. We do projects like this to figure out how to make it accessible and practical for all kinds of use cases. And I think the best person to talk to you about that is a student. So I'd like to introduce Nicole Pelizin, who is studying at the Imperial College of London. She's studying aero engineering, and she's going to talk about her experience using generative design with a small component in the context of a really admirable goal. So please welcome Nicole.
Morning, everybody. So Aviation has really changed the way in which we travel. Over a span of 50 years, there's been a 400% increase in takeoffs and landings in the UK. It accounts for 13% of CO2 emissions from EU transport annually. And with climate change progressing at the rate it is, we can't ignore any single sector. So whilst this can be tackled with increasing engine efficiency, hybrid aircraft, and eventually fully electric aircraft, we can also go back to the age-old conundrum of how can we make our aircraft lighter? And this is where generative design comes in. So I chose to consider this small and inconspicuous part, this bracket that attaches the tray table to the seat in front, to see what generative design could do. And what I discovered is that generative design is so much more than just topological optimization. From a single input, multiple outputs can be created, each suited to a different manufacturing method or material, but they are all completely valid. So this allowed me the flexibility to pick this design, which I have here a 3D printed prototype, but it is actually also capable of being 5-axis milled. So this crazy and alien-looking part is actually fully accessible to current manufacturing technology. To push this even further, a mold could be made, and these brackets could be cast, just like the JPL concept lander Morgan just mentioned. So, manufactured in aluminium, the original bracket weighed 784 grams. With generative design, I was able to reduce the weight to 367 grams, which is a weight saving of over 50%. But on such a small part, does this really have an impact? I won't bore you with all the maths, but I will give you a brief overview. So we can consider either the Breguet range equation or specific air range of the aircraft. I personally considered the latter. And to simplify things just a little bit further, I then only considered the cruise portion of the flight, which is where the aircraft will spend the majority of its time in any given flight. So drag is in fact proportional to weight, so by decreasing the weight of the aircraft, we decrease the amount of drag it experiences. In other words, it has a smaller resisting force against its forward motion. So, to keep it moving in the same way as before, we need less thrust, and less thrust means less fuel consumed, which we can quantify in fuel mass flow rate. So, take the example of a London Heathrow to Tokyo Haneda flight, which, for example, British Airways services with the Boeing 777-300. At the aircraft's maximum capacity of 550 seats, the total weight reduction from installing the generatively designed brackets is 459 kilograms. Plugging in all the numbers and computing the calculations gives a fuel mass flow rate of old to new, ratio of old to new of 0.9943. So assuming that our airspeed remains unchanged and we can say that the cruise time is the same, for both aircraft, we will therefore get a fuel reduction of 0.57%. So if 136 tons of fuel are burnt during the original cruise, 775 kilograms of fuel will be saved, which is about $482 per flight. BA runs this route on average 28 times a week, which leads to an annual fuel cost saving of $702,000, which from an emissions perspective is 2.4 tons of CO2, which is roughly the equivalent of 1.7 cars with their annual emissions. And I know 1.7 cars doesn't sound like much, but we've got to put this into context. This case study considered 1,500 flights throughout the course of a year. In January alone, just in the UK, there were 221,000 commercial flights. So there are enormous potential savings in both fuel cost and CO2 emissions from something that is really quite small and simple to scale up and implement. So I really look forward to seeing what the aviation industry can do with generative design. And I hope that when I graduate, I will be able to continue to develop green solutions such as this. Thank you.
Thanks, Nicole. Did I mention Nicole's a second-year student? It's amazing what she's already doing. I asked her yesterday, how long does this project take you? She said, about 40 hours, the whole project. most of that time was doing the research on the numbers and doing the math, not on geometry creation. And the reason Nicole spent most of her time doing that was because she's looking to figure out, is what I'm doing making an impact? Because that's what Nicole's in this to do. She wants to know, can I make an impact in this industry? So when Nicole graduates in 2 years, and she goes into industry, what will you do different to bring in that kind of talent into your company? Imagine what would be possible if you gave Nicole the creative freedom to look at a much larger problem across the whole concept to manufacture product process. And the thing is, there's always been these traditional limitations to creative freedom. One is task-based tool sets. We've been designing solutions for a long time that are desktop applications that are very specific to one particular thing, for additive support systems or for a particular toolpath, for rendering. And these tools are incredibly cumbersome to exchange data between. And with complexity rising and with the tasks themselves changing, this is an unsustainable way to think about things. The second limitation is siloed domain knowledge, and the third is time. And so when you couple siloed domain knowledge and the amount of time you have as limitations, it's no wonder that we make decisions for design based on what we know or based on what our experiences are, because we don't have enough time to go and explore all of our options. You know, talking with Nicole made me remember my first time going through the design through manufacturing process. It was about 6 years ago. I was a summer intern at Autodesk, and my first day, I remember them sitting me down in front of the computer, and they said, "We want you to try this beta software. It's called Fusion 360. And at the time, it was this hybrid industrial design and mechanical design tool, and it was the very first 3D modeling tool I'd ever used. So it was really fun. I went through the whole process of coming up with an idea and manufactured the whole thing throughout the summer. And at the end of it, I remember talking to some engineers, and they said, "What you did is really interesting because this is not what I'm used to. I'm used to having to do parametric modeling and surface modeling in separate tools." And I remember thinking, what? That's ridiculous. I can't imagine having to be limited in my process by the task. And so Fusion allowed me to combine these tasks, and it broke down the silos between industrial design and mechanical design, and it gave me back my time. And over the last 6 years, we've been executing on this vision and keep raising the bar so that we can build a fully connected concept through manufacturing product process that is not based on the task, but it's based on the process, because that's what we're all doing, and it's going to give you the flexibility to design your own process so you're not forced into one. So this is the goal of Fusion. Eliminate task-based solutions so that you can have a fully unified end-to-end product development process that's customized for you. Now, we live in a global world, so I can be in San Francisco, where I'm based, seamlessly collaborating with someone in the UK. And we can see any changes made to the models, version updates, see why those changes were made. I can go in and say, hey, I came up with the specs for the tires, added them to the design. Will you go ahead and move forward with the fender design? My colleague in the UK might say, yeah, no problem. I can start doing the concept modeling, using surface modeling tools, go into the detailed mechanical design. And because it's a fully connected digital pipeline, everyone can see any changes made to the design because we are all collaborators in the process and all the decisions are impact each other. So downstream workflows, we can end up doing detailed documentation for our manufacturing vendor. I can go into our validation workspace and use our portfolio of simulation tools. And I can utilize our suite of CAM tools to build a manufacturing plan. And because this is a cloud product, of course, I can access this on a Mac, on a PC, or on a mobile device. So Fusion is not just CAD. It's not a render. It's not a simulation tool. It's not generative design. It's not a documentation tool. Fusion is a fully connected, unified product development process platform so that you can design your own process the way you want it to. So to talk about this integrated process, I want to introduce you to Will. And Will, saw a lot of their product in the prior videos, designs and manufactures personal electrical vehicles for those with physical impairments. Their goal is to empower their customers to be able to fully enjoy and explore the outdoors with independence. The way Will has designed their product is it breaks into 3 different modules so they can break it down and pack it in their vehicles when they move about. So one particular module holds the batteries because it's an electrical vehicle, and that module is the heaviest. And so they were looking for something to help them get under the goal of having every module be under 15 kilograms. So using generative design, they started an exploratory process. And they said, okay, there's a number of different materials we might consider based on cost, performance requirements, and weight. There's a number of different scenarios in which this vehicle might endure. It might hit a bump in the road, or there might be some impact during shipping, and we want to make sure it gets the customer in perfect condition. There might be some things that have already been locked into the design, and they'll mark those as obstacles in red in the design space, and then there's the preserved geometry they want to keep intact. And then there might be certain manufacturing options that they are specifically wanting to deal with. So do they have access to a Haas machining center? Do they have access to a plasma cutter, to a 3D printer? All these different manufacturing methods have different trade-offs. So when they actually push that out, they don't get only one option or 5 options. They get dozens, if not hundreds, of different options that meet those criteria. So in Fusion, the way this actually works is as soon as it's set up, the user hits generate. It pushes out to our system. The algorithms generate tons of different options that also meet this criteria, and it sends the user into this explore environment. It's a data visualization environment that helps a user diagnose trade-offs and browse the different options within the design. Once they start to find a design they really like, they can export that design into the assembly to have context, and it's not a mesh. It's CAD-ready geometry that they can fine-tune to their liking. They can beef up a particular strut or edit the global curvature of the design. Now, any edits that they make to this design, they can, of course, further validate, maybe doing a buckling analysis or a nonlinear static stress. And then there's all the tools they have to do the manufacturing process. So Will, at the end of the day, designed this part, and it ended up being 40% mass savings to the original design. Now, I had the pleasure of seeing it in person last week in San Francisco, and the team's incredibly excited about this process because they're starting to think about how this mindset will allow them to design any given part in their system. We're also looking at other manufacturing methods, more traditional manufacturing methods, and incorporating that into our generative algorithms. For example, we're looking at 2-axis cutting, a very traditional manufacturing method. And in Fusion, when we introduce these new methods, it's going to appear just in the toolbar, just as the other ones are, alongside additive and 5-axis milling, which you saw Nicole talk about, 3-axis milling, and 2-axis cutting is now in there. And the reason we want to do this is you should be able to make a selection of these traditional manufacturing techniques against these new manufacturing methods because they have different benefits. And when you actually go to manufacture it, the tool sets for doing something like a water jet toolpath are already in the system for you. So I'd be remiss to not talk about what we're doing around adding more advanced manufacturing capabilities into Fusion because that's really core to converging design and manufacturing. And not too far from here, out in Birmingham, we have an advanced manufacturing facility that is known for pushing the limits around machining and robotics for years. They have great products already out there, specialty products like FeatureCam, PowerMill, PowerShape. And what we're doing is taking some of the most favorite features of these products and bringing them into the Fusion family. And we're adding that by creating an advanced manufacturing extension. So when you're in Fusion, all you have to do, if you have a need for specialized capabilities or new manufacturing methods that you want to, new manufacturing capabilities that you want to test out, you can go in, turn on the advanced manufacturing capability, and the tool adapts to your particular task. And so you'll now have access to the steep and shallow tool path. You'll have access to feature recognition for automated toolpath creation, for surface inspection, and for the first time, a fully hybrid additive and subtractive workflow in one environment. When you're done with these capabilities, all you have to do is turn that extension back off, and the tool, again, adapts back to your workflow. So what does design and manufacturing convergence enable? It enables JPL to design landers to go way further into space than they could have imagined. It lowers the barrier for someone like Nicole to make an impact on CO2 emissions and a company's bottom line. It enables a startup like Will to create products that empower their customers. And I want to remind you that everything I talked to today is available right now in Fusion. And you don't have to go very far to see the adoption. Here at the University of Sheffield, what they're doing is creating spaces like iForge that have multidisciplinary design, different engineering teams coming together to work on projects, and the natural tool of choice is Fusion 360. So we're incredibly excited to partner with them. We really look forward to working with them in the future. And it's exciting to see machines like these Haas machines downstairs that have not been used for years now online because Fusion has lowered the barrier to entry to create tool paths to actually make finished products. And Nicole isn't the only one that's doing work around generative design. Upstairs in the exhibition hall, go talk to the folks at the University of Warwick. They are designing semi-autonomous vehicles and using generative design to drive the topology of their structure, and using the manufacturing capabilities to create their manufactured products. Definitely encourage you to go and talk to Robbie, because I heard a really amazing example of comparing topology optimization to generative design, and generative design just blows it out of the water. So go ask about that. Now, these might seem like edge cases. We talked about students, we talked about a startup, we talked about NASA. So who else is using Fusion? Companies of all complexity and sizes are finding a better way to work with Fusion. You see industrial design companies like Steelcase and Fabric who are doing anything from surface modeling all the way to downstream manufacturing workflows. You see startups like Modbot, a robotic startup that needs multidisciplinary design tools, Fusion, and even high-end manufacturers like General Motors that are using generative design not only to explore additive, but also things like part consolidation. So I'll leave you with this. Imagine what your world would be if you didn't have to do data exchange between tool sets, and instead your tool adapted to your task for you and grew with you. Imagine if you didn't have these siloed domains in your industry, in your company, and you now had access to this expert knowledge and can incorporate that into your innovation cycle. Imagine if you had more creative capacity because you could partner with your tool to come up with a much wider range of solutions for your designs. What would you do then? Thanks.